doctor?
نعم.
Can you please repeat briefly طلعت constant acceleration?
Yes, sure. Because look here in your system, you have two blocks connected by a system of pulleys. Okay, what will drive the motion here is what is the weights of A and B. Okay, so depending on the weight of A and B, the acceleration will change. Because the weights are constant, okay, we are not changing them, so they will induce a constant acceleration of the system. To induce variable acceleration, you should have a variable force. And for example, if you apply a force here that is variable, let's say you are putting a force F, function of time here. So if I tell you the applied force at A is F equals to 2T, for example, then when you solve your system, you will have the acceleration and tension function of time. But because you have a constant force that is driving the motion, then you will have constant acceleration at the end. Okay?
Okay, doctor.
Any other question on this? Okay. So let us continue. So until now, we have considered application of the second law of Newton in rectangular components. As we have seen together in the previous chapter, depending on the problem, we might need to work in other types of coordinates. And the most used one is normal tangential coordinates, which is used in general when I have curved motion. So in case I have a circle, or in case I have any curve, because we have seen together that if I know y function of x, I can determine the radius of curvature at any location. Okay, so the second type of Newton law application is writing equation of motion in normal tangential coordinates. Okay, in this case we have already seen together the frame u and ut. But here, when we want to apply the force relation, we should add a third unit vector, ub, which is perpendicular to u and ut, as you can see in this figure. Okay, why we didn't talk before about ub? Because when we defined u and ut, we said that it is the instantaneous plane of motion. So what do we mean by that? At any position p, okay, you can consider that I am moving on a small arc of circle. Okay, so let's say when I am here, I was moving along this circle. Okay, when I am here, I am moving along the arc of another circle, and at each location, of course, I have a certain radius of curvature. Okay, now what is u and ut? At any location, u and ut is the plane of the circle. So when I was here, for example, ut was tangent to the path, so it's perpendicular to the radius, while un was directed toward the center of rotation or center of curvature. So this is my u and ut. Okay, of course manna to scale هن unit vectors. So we can say that at each instant u and ut represent the plane of motion. Now why in 3D we need to define a third coordinate, يعني a third unit vector اللي هو perpendicular to both. So here if you have this is u and ut, the perpendicular to the plane of the circle of motion is ub. And ub is very important sometimes because it will give us an additional equation. To facilitate this on you, if you remember, if we consider a ground, a flat ground, and we have a box, the box is moving on the horizontal ground, so I only have acceleration along x. But why I need, sometimes why I need to apply some of y? So for example here, if you have the weight, and if you have the normal, and if you have the friction. In general, when I have kinetic friction, the friction and normal are related. So to calculate friction, I should know normal. And I cannot find normal if I don't do sum of forces along y equals to 0. So y equation will will give me an additional equation to get one of my unknowns. So even if I don't have a motion along a certain direction, it's useful to write sum of forces along this direction equals to 0. This is why now we should introduce the third unit vector. So in normal tangential coordinates, we have the t-axis, which is tangent to the path, as you can see here. We have the normal axis that is directed towards the center of curvature. And this plane, okay, UNUT will contain the circle containing the arc, the segment of circle I am moving on at this instant. And UB will be perpendicular to the circle, so it will be perpendicular to the plane UNUT. Since UB is perpendicular to the instantaneous plane of motion, then I can say that sum of forces along UB is 0, because I am not moving along UB, I am moving in plane UNUT at each instant. Okay, so the three equation of Newton law in UNUT will be sum of forces along UT equals to MAT. And from the previous chapter, you know that AT is dV by dt. It will represent the change in speed, okay? While UN is due to change in direction. So sum of n is equal to MAN, and AN can be calculated as V square over rho. And finally, we have that sum of B is equal to 0. This is the third relation along UB, since no motion along UB. Okay? Now, always remember that you can use all the relation in the previous chapter if you have a certain additional unknown. So, for example, if you don't know the radius of curvature and you have y function of x, you can use the relation we developed previously together, that the radius of curvature is given at a certain position x by 1 plus the first derivative of y with respect to x squared, the whole term to the power 3 over 2, over the absolute value of the second derivative. Now, let us do an application, a problem of application on UNUT-UB. Determine the banking angle theta for the racetrack so that the wheels of the racing cars will not have to depend upon friction to prevent any car from sliding up or down the track. Assume the cars have negligible size, a mass m, and travel around the curve of radius rho with a speed v. So here, to imagine this problem, all of you watched Formula One. When you have Formula One, how the race in general is, it's not a horizontal race. If I draw for you the profile view of the race will be like this. It's an inclined race, okay? And the angle of inclination of the race is designed in a way to facilitate motion. So we can have motion with constant velocity without depending on friction, okay? How to do this? We will see in this problem how we can do a preliminary design of what should be theta in order to move without depending on friction. So this is the angle theta, and this is my car. Now, the wheels of your this is the wheels. The wheels of your car, okay, are inclined relative to the horizontal, but the plane of motion is the horizontal plane. Why? Because if you look from top, in case of Formula One, when they take top view, you will see that cars are rotating on circles. If you look at the figure here, شوين باينين circles, you have dashed lines. يكونوا مرسومين على الريس dashed lines, which will lead to circular tracks. Okay, so each car will go over a circular track. So if you look from top, you will see that the car is moving along a horizontal circle. Okay, but its wheels are inclined with a certain angle relative to the horizontal surface. So if I want to draw here the free body diagram, so this is my car, okay? This is our car. What are the forces acting on it? So first, of course, you have the weight, the weight which is vertical. And what also? What are the other forces acting on the car?
Reaction.
Yes, exactly. The reaction, how is the reaction of the ground on the car? Always
Inclined by
reaction,
delta.
eh, the reaction is always perpendicular to contact. Here they told us neglect the size, okay? So we will treat the car as a particle because they said neglect the size of the car. So here, if you want, if I draw it here, I will consider I have a particle. This particle is subjected to a weight and to a normal. The normal is the resultant, and you have, of course, at the wheel level, you have the normal, but you can replace it by a resultant force since we are neglecting size. So here I will just put N. So I will model my system as a particle subjected to two forces, the weight and the normal reaction. Okay, now, do I have friction here? Do I have to add something else? They told me the car should not depend on friction, so no friction. And since I'm moving at constant speed, so here also I will not consider the engine force. If I have in general, the engine force will give me a certain acceleration. So only I am relying on the effect of my weight and the normal. So of course I have a certain transition phase to accelerate my car. And once I reach a certain speed and I want to maintain the speed, I will remove the engine force, okay? And I will just move under the effect of N and W. And I should demonstrate here what will be the relation between the velocity I will have and the banking angle theta, okay? Now, in which type of frame will I work here? XY, UNUT, URU theta? What should I choose? What do you think? In which frame I should work? In general, okay, when you have circular motion, always use UNUT. And UNUT is a very good frame to use in circular motion. Why? Because already you know that the radius of curvature is equal to the radius of the circle. Okay, so you know already an function of v and rho. An is v square over rho. While here in this problem, what will be at? What will be the value of at? To know what will be the value of at, let us try together to put the coordinate system. Okay, first I will draw it for you again on the two views. I will do it on top view for you to see it better. Then on the profile view. So this is the top view. And this is the profile view. If you look from top, you will see that your car is moving on a circle, a horizontal circle. Okay, so you have that. This is my car. I will deal with it as a point, as a particle. Since it's rotating on a circle, then I will take ut tangent to the path, perpendicular to the radius. So this is vector ut at a certain instant, if my particle is here. So this is ut. How is un? Un is always directed towards the center of curvature. Okay, so if my center, the center of my circle is here, let's say, then I have that UN is directed towards the center. So this is UN. And how is UB? How is UB vector?
Perpendicular na po.
Exactly. We said that UB is always perpendicular to plane of motion. And if I want to illustrate it here, it is, I put a circle with a point. يعني هو is perpendicular to the screen towards you. So this is UB. Okay. Now, on the same graph, I will represent forces. Okay. My forces, to see them better, I will first represent UN UTUB on the profile view with the forces. So, on my profile view, UB is vertical. So, if this is my particle, if my particle is here, let's say, UB is vertical upward. If you take it up or down, it's not an issue because sum of forces along UB is 0 and it doesn't matter if you take it up or down. Okay. So this is UB. How is UT, guys? On the profile view, how is UT? Imagine that you are looking at the car. The car هتبين عم تجي towards you, okay? Because it's turning. So it's turning like this. It's going towards you, turning and then entering the screen. هيك عم تبرم. So this is why إذا بتتخيلوها, the car is coming towards you. يعني UT is perpendicular to the screen in the profile view. So I will draw it as just a circle with a point. So this will be UT. And how is UN? نحن قلنا الموشن بهوريزونتال بلين. هون انتم ما بتشوفوا من الهوريزونتال بلين الا اذا بدكم البروجكشن. The projection of horizontal plane here is a line. So O is somewhere here. You can see O. O will be somewhere here. And UN will be directed towards O. So this is UN. Once you do this step, the problem will become very simple. Okay, because the most important step is to put your unit vectors. Once done, it's only projection. You still only have to do the good projection. So now, after I determined how is my unit vectors, I will represent my forces again. So my particle is subjected to the weight, and it's subjected to the normal reaction that is perpendicular to contact. So this is W, this is N. So as you can see here, I don't have force projection along UT. The two forces I have are in plane UN, UB. So when I do sum of T, what I will obtain what? Sum of T equals to 0. This means that AT is 0 and therefore my velocity is constant. Okay. Now, concerning W, W is only along UB in the negative direction, while the normal here is having two components, one along UN, one along UB. We will see together انه ال N, the component of N along UN هو اللي حيخليني ابرم. يعني it is the normal reaction that will drive my motion here. Because look, when we will write sum of N equals MAN, the only contributor to AN will be the normal force, since the weight is perpendicular to UN. So here, because my هيدي inclination of the plane هي اللي بتساعد الcar to move without relying on friction. Okay? So now, if I want to represent these forces بالtop view, the profile view is better for you. يعني انتوا بس تعملوا projection, look at the profile view. But in case you want to put them in the top view, بالtop view هيكون الويت perpendicular لجوا. يعني you can replace it by an X like this. This is the weight. Okay, يعني it's only along UB. بينما النورمال will have two components. So for your normal عجقت شوي الفيجر. اوكي فما راح احطها هون لانه حتعجق لكم كثير. النورمال عندها two components. One along UN, one along UB. ما حتقدروا تقشعون مزبوط بالtop view. This is why the profile view here is better to work with. Okay. Now, in order to project the normal on UN UB, I need to know the angle. And since I know that this angle here of the inclined plane is theta, okay, and we have here these two angles equal, يعني هيدا كمان theta. So this is theta. So the angle of n with UN will be, this will be pi over 2 minus theta. And this will be theta. So if you want, n is doing an angle theta with UB and pi over 2 minus theta with UN. Once I determine this, all I have to do now is to apply the projections. So let us apply together the three projections. Let us go down. So this is the illustration we did together. This is the profile view of our car. As you can see, forces are in plane UN, UB. UT is perpendicular towards us. We have that the weight is downward along UB, while the normal is doing with UB an angle of theta. So now let us write together the three equations. The first equation is sum of t equals MAT, and AT represents dV by dt. Since we have no forces along UT, so sum of forces along UT will be 0. So we will deduce that V is constant and AT is 0. This is the conclusion we can make from the first relation. The second, and it will not help us here in this problem, and here we want to find a relation with theta. So we need other equations. The second equation to use is sum of forces along UN equals to mass times AN. And because we know the radius of curvature here, it is the radius of the circle. So let's say O is here. They told us that the radius of curvature is rho. So we can write that AN is V square over rho. So here, if we replace, it's M times V square over rho. So now I should project on UN. The weight is perpendicular to UN, so no projection along UN. I will only have the component of the normal along UN. So I will represent it here. If you project the normal along UN, you have to do n sine theta. Okay? So I will write here that n sine theta, n sine of angle theta, is equal to m times V square over rho, which is the radius of curvature. I will write it here. So this is equation number 1. The second equation to write is along UB. Okay, so I have already written the equation along UT, the equation along UN. So this is UT equation, this is UN equation. Now I will do the relation along UB. And we know that sum of forces along UB is equal to 0. So sum of B equals to 0. What do we have along UB? Along UB, we have the projection of the normal and the weight. So plus n cosine of theta minus W, so minus mg equals to 0. This is equation number 2. Since my purpose is to determine the expression of angle theta, so From first relation, I got that n sine theta, so I will write my result here. N sine theta is equal to mv square over rho, while n cosine theta is equal to m times g. So to obtain theta, all I have to do is to divide equation 1 by 2. This will eliminate the normal reaction. Okay, so by doing equation 1 over 2 will give me that tangent of theta is equal to m is simplified, so it's v square over rho times g. So as you can see here, you can calculate angle theta as tangent minus 1 of v square over rho g. So in general, if you want to design your race, you can start with this approximation. So let us say I want to move with a velocity of let's say 150 kilometers per hour without relying on friction. You replace v by its value, and you get an approximate value of the angle theta that should be used to achieve this velocity without relying on friction. Okay, so you can see here all details we did. So as we did, we projected on u and ub, then we divided the two equations. We got the value of theta as tangent minus 1 v square over rho g. Any question on this problem? Okay, so let us continue with another problem. The design of the ski requires knowing the type of forces that will be exerted on the skier and his approximate trajectory. In the case shown, determine the normal force and acceleration on the 600 Newton skier at the instant he arrives at the end of jump A, where his velocity is 9 meters per second. So here we have the figure. We have a skier going down a certain curve. The equation of the curve is given, so y as function of x, and we are just interested at what is the tangential acceleration at point A and what is the normal reaction at point A. Okay, so whenever they ask for a specific point, then you take the point of interest and you draw the free body diagram at this point. So when the skier will reach this position here, first you have here that ut is always tangent to the path, and at A the tangent is horizontal. So you can say that at this point ut is in this way, it's horizontal, and un is directed towards the center of curvature, it's perpendicular to ut. كيف عرفنا انه center of curvature لفوق مش لتحت؟ من ال shape of the curve. هلا sometimes it's hard to see it. ساعتها بنجيب second derivative. Okay, if the second derivative is positive, هون it's a constant, it's a positive constant here. The second derivative here, we will calculate it together, it's always positive, so the concavity is upward, يعني un على طول لفوق. Sometimes in some functions you might have change in concavity. So when the second derivative is positive, un will be up. When the second derivative is negative, un will be downward. Yani for example, if you have this curve, okay, in these locations here, un will be downward. In other locations, it will be upward. Okay. Now, so here you can see the free body diagram at point A. So as we said, ut is horizontal, un is perpendicular upward, and At this location, the forces acting on the skier are its weight and the normal reaction. Here they gave us the easiest point. I will do for you the general case after we finish the problem. Okay, so they can ask you for any point in between and we will see how to do it. But at A, the two forces will be along UN. Here, if you want, UB is perpendicular to the plane, but we will not need it. You know why we will not need to do sum of forces along UB here? So this is UB. UB is towards us. But why we will not need to do sum of forces along UB? The equation will not give us anything. Why? Do you have any force along UB here? When UNUT contain all forces, you will not use sum of B equal to 0 because already all forces are in UNUB. So no need to project along UB. This is the case here, which was not the case in the Formula 1 example. In the Formula 1 example, the normal has a projection along UB. So you will need the equation along UB. So in general, when all forces are in UNUT plane, no need to use sum of forces along B equation. While in case the forces are not in the plane of motion, as it was for the previous problem, then we need to use sum of forces along UB. So here first, to get the normal reaction, NA, we will use sum of N. Sum of N equals MAN. From this relation, we have NA is along positive N, so plus NA, and minus the weight, minus 600, equals to the mass of the skier, which is its weight over G, times the normal acceleration. The normal acceleration is V square over rho. Here they gave us the velocity at A, and the radius of curvature can be calculated based on what? Based on the formula we developed together in previous chapter. So we said that if we have y function of x, we can calculate the radius of curvature by calculating the first derivative and the second derivative. So the first step here is to find rho at A, and then we replace in the equation to get NA. We will do the calculation together. But just before doing it, in order to find the second unknown, which is AT, we need to write the second equation. The second equation here will be sum of forces along UT. And here UT is directed towards the left because the skier is moving in this way. So here V will be, UT always follows the velocity, and the velocity is towards the left, so UT is towards the left. This is why here, when you write your equation, you will specify the direction of UT. So sum of T equals to MAT. Since I don't have any force along UT here, because weight and normal are both along UN, I can deduce that sum of forces along UT is 0. So in this particular point at A, the tangential acceleration will be 0. So AT is 0. Now, concerning the normal, to get the normal, as we said, we need to determine the value of the radius of curvature. So to calculate the radius of curvature, I will use the following formula, that 1 plus dy over dx squared, the whole term to the power 3 over 2, over the absolute value of the second derivative equals to the value of the radius of curvature. So now, to get the radius, we should find the first derivative and the second derivative at point A. The function is given, so it's very easy. We derive it. The derivative of 160 x squared minus 15 is x over 30. And the second derivative is 1 over 30. So as you can see here, the concavity is always upward because the second derivative is positive. So UN will always be upward. So now, in particular, we are interested at point A. A is characterized by x equal to 0. So dy by dx will be 0. And the second derivative will be 1 over 30. So if we replace back in your equation, dy by dx will be eliminated because it's 0 at A. You will only have to replace the second derivative by 1 over 30. So rho will be equal to 30 meters. And now, replacing back into sum of n equals MAN, rho by its value, you get the value of the normal reaction at. And here, since also we need to determine the total acceleration at point A, don't forget that in curved motion, the total acceleration is divided into tangential and normal acceleration. And we developed together that AT is 0. So the acceleration at A will be restricted only to AN. And AN can be calculated as V square over rho. So this will give us the acceleration of A at which is only equal to AN. It's along UN. It's upward, therefore. It's equal to 2.7 meter per second square. So here, if you want to represent the kinetic diagram, if we go back to the figure, the kinetic diagram at point A will be like this. We have only mass times AN. So this is M times AA at this location. Okay. So I will just open a new session, Zoom session, to tell you what we will do if we have any arbitrary position in between. And if we will not work at A, at any position in between, what should we do? So the time will end. I will open a new session.